Well, gentlemen, let me just say that what we're going to work on here today is a repurposed SP220 cabinet with an external power supply. This has got three, 1, 2, 3, or as the Germans do it, 1, 2, 3. Three 500Z tubes in it. Okay. Also, let me apologize for the sound of my voice. I am trying to recover from a cold, and intermixed with all the other responsibilities I got going on, my elderly grandmother's not doing so hot. I've been running over and spending most of my days with her, but we're going to give this a look for her. So, like I said, if I cough, if I hack, if I wheeze, no, I'm not dying. I'm actually recovering. This last weekend was really rough, so we're over here taking a look at this here today. So just bear with me. It's going to be okay. Let's see. The main complaints were that he couldn't get it to do more than 1,000 watts. It had a bad high voltage hum in it, over the air transmitting noise, and it just didn't seem to be right. And he said every once in a while you'd see some arcing from down here inside the cabinet. So we're going to take a look at the power supply, and we're going to take a look at the amplifier, and we're going to figure out how this whole thing's wired, and we're going to go through it from top to bottom. So I'm going to cut this segment off. We're going to slide the armor off. We're going to take a look at the inside of the RF deck and its layout, and we're going to slide the top of the power supply off, and we're going to take a look at it. Like I was telling him, 9 times out of 10, when you hear a humming noise coming through the transmit side of somebody's tube amplifier, usually what that is something to do with the bleeder circuit, or not bleeder circuit, the capacitor bank. It's either too small or you've had a cap go open up and go bad, and you end up getting a hum. A little bit of AC ripple will leak through the power supply, and it'll present itself as a hum on the transmit side. So take a hot eyeball look at this and a hot eyeball look at this. Let's get this opened up so we can take a look at what's going on the inside, and we'll go from there. So away we go. Well, this is a pretty straightforward transformer. They have it Quasimodo wire-fied for 220 here. So contactor fires, gauges transformer, no soft start circuit, full bridge rectifier going directly into a selectrolytic bank. Each one of these caps is 450 volts a piece, which works out to be about 3,600 volts. Oh, excuse me, top voltage. So, of course, we can't run at 3,600. We got to give it a little bit of headroom of a couple hundred volts, so like 3,400 volts max. These are 470 UF worth of filtering per cap, so then we're going to take 470 and we divide that by 8, which gives us roughly 56 point something, so we'll say 60 UF, which is more than enough. We want to keep it above 16. Anything below 16 and we're definitely going to have ripple. So the only thing that could happen is that maybe a couple of these caps have gone low. I don't see any sign of leakage or anything. But we don't really know until we run it to see what we've got for high voltage that comes out of this thing. Very creative little bleeder circuit, but this is a high voltage rectifier circuit at its absolute finest. Most minimalistic parts that you possibly can have. There's no glitch on the ground, which is this lead here. Goes directly to the case. It looks like the brown and the green wire here are our ground returns that go up to our remote plug. Our red lead here is our high voltage, so that makes me concerned. Now let me explain to you why. This lead here has got an insulation value of about 600 volts safely. So double is 12, 4 times 24. So we're asking this to insulate for 6 times this amount of electrical ability. That scares me a great deal. That and there's no safety circuits on this thing. I mean, at a minimum, we've got over here on the front, we've got these holes here. We could put a fuse, and we could short fuse it for, let's say, like a half amp or an amp. And we'd do that on the ground side. So these leads, and then on the high voltage positive side, we'd want to run it through a glitch resistor, probably 1.5 ohm, 1 ohm, something like that, probably 300 watt, 400 watt, something like that is what we'd want to have on the positive side. That way if there's a short or something breaks down or the diodes open up or there's something that happens over in the RF deck, it's either going to wipe out the ground side of the supply, which will isolate the high voltage supply. And then that huge electrical impulse that's going to come from that short can get absorbed inside the glitch resistor. The glitch resistor, in some circumstances, you want it to be a sacrificial animal, a little sacrificial device, something that's the weakest link in the chain so it blows completely apart like what they do on the SP220s. On this style of power supply, you'd want it to be an absorbent, kind of like a shock absorber to the circuit. And it'll help protect your diodes from any return rush current that might come back and whack your diodes out. So it'll save you from having to rebuild your diode board, but in the same breath, it's going to help protect you physically and your tubes. So no safety circuit, but in theory, and listen to me when I say this, in theory, this supply, this filter cap, is adequate to do the job. As in there's enough high voltage and enough capacitance. Now we're going to run it as it sits, and I want to measure a couple things. First, I want to see what I have for plate voltage, and if it's over 3600 volts, and then I know that the reason that we've had the ripple taking place is that we're running right past the capacitor's ability to be able to isolate and snub out that ground, not ground, but the AC ripple. I do see a couple things here like that could possibly be touching on this case, but yeah, it is what it is. All right, let's slide this out of the way and let's go take a look at the RF deck. Okay, go. So I have times where I feel really good, and then I have other times where I just feel like I'm dying. I'm feeling like I'm dying at the moment. All right, so the plate transformer has been removed. The filtering cap circuit has been removed, obviously. It's been replaced by that. This is what we call your basic conversion. Yes, it does have 3 tubes in it. The thing is they left the band switches all in play. The input and output band switches are all still in here, as far as I can tell without pulling the face off, which we're going to do here in a few minutes anyhow. They're still fully functional. So in theory, we could run this on all the different bands. In theory. My customer doesn't want to run this on all the bands. All he cares about is that one that's between 12 and 10 meters, right? I've gone on to explain to him that if we drive this thing to what it needs to be driven with for its full potential, that this is going to fail him and that's going to fail him. So to save the most valuable part, which is the input band switch, we're going to save it for the next generation. We're going to remove all of this. I got the length of the tank coil wrong. At some point the coil, which should be tapped here, has gotten moved over one and soldered onto here. The bottom side, let's go look at this for a minute, has got just as many problems. Not really problems, I mean the basic characteristics of this stuff is here. It's got grounded grids, kind of got added ground grid here, and it's grounded and grounded and grounded. The input coax is not the greatest. It's RG58, so we'll probably change that out to RG400. The relay will easily do this job, although we can see here on one of the pins that it's seen some heating in its day. We can see that this tab here is what carries the RF, and it switches from the bypass mode down to this piece of coax. This is not soldered, as we can see. And this over here is just flat out not even attached to anything. It's just floating free in the case, and it's melted. So, and this coax connector is as black as you can get, and it's hogged out. So, at some point or another, this coax connector has gotten hot and lost contact. The filament choke, getting a little warm, but as we know after our conversation with the great and legendary Yellow Jacket, that will easily do what we're wanting it to do. I am grateful that the breakers over here are still in play, and as you can see here, filament choke has gotten a little discolored, but it'll take what we're doing. We can't do a 4-tube this way, but it'll handle a 3-tube. And the stock filament transformer, as we know, can handle up to a 4-tube, but anything past that, then you need another filament transformer. So it just dawned on me, where's the bias circuit in this thing? There is no bias circuit. The zener for the center tap has been removed here. Oh, this board here, this is what's left of the high voltage rectifier board that's stock. I did test this meter, it still works, but the way they've got this set up is that the high voltage comes in here by this bypass cap, which is still relatively hard. We'll do a leak down check on it. And yeah, it's screwed in. Anyhow, the high voltage comes in here and then it flows back, goes through this pass-through, and is supposed to run this meter so you can see what you got for plate volts. In theory, it should work. In theory. This is our lead that would go off and go to our bias, but they've got it grounded through these chokes. So the grounding the grids on the 3500, that's not going to work right. Huh. Okay, so we got some problems that we've got to overcome. Some small electrical issues with the coax, and I mean, we can, with 3 or 4 10A10 diodes, we can get a good, decent zero signal going on. We really can. And we can get this to drop to the proper cutoff voltages and go from the high voltage down to the proper operation voltage. So I don't know why this would never work. This would never work. I don't see anything in here that's going to go like zip, zow, pow, bang, boom for the most part. This is the scariest bit to me. This is our high voltage lead. We'll probably have to break that out and we'll have to do something independent. I don't know if I got any more Molex high voltage pass-through nuts. I should have a couple on that shelf. I'll have to go digging for them, but I want to hook this up and turn it on and watch it run for a minute, and I really want to measure our high voltage over here and see what we've got going on for filtering. Well, we are going to change that. We've got to add a minimum of 3 fuses, one for the ground on the high voltage, and then the 2 for the 220 leads coming in. We can't just bring it in and bring it straight to the contactors. We have to have some kind of safety circuit that's present there. Either it be breakers or I'm going to go with fuses. And yeah, we'll install a glitch over here. But I don't see anything that makes me want to cry too awful bad, but there are some things that make me scared. So this is our center tap lead, and it runs up and it goes to here. It's going to here. That's off, engaged. So 120 volts for cutoff, then engaged reference to ground. It's probably why this thing wouldn't take off and run so hot. I mean, if it did, these tubes flared up pretty quick. This has kind of got me a little interested here. What's going on the back side of this thing? This is the appropriate style cable coming out the back. No grommet, of course, Because I mean, why would we want to have a anti-rub piece of rubber next to something that's got unfused, unprotected 110 volt going through a cabinet? I mean, why would we want to just put a grommet on this? But this is kind of scary to me. I don't know about you all. I mean, this might be totally acceptable for you all, but this makes me rethink things in the world. Yeah, we'll come back to that too. The other thing is none of the tubes show any sign of it yet, but they will. There's no air circulation on the bottom side of this cabinet, none whatsoever. And even though this is high temp solder, unless there's some kind of airflow that goes across these pins in some way, these pins can get hot enough and the solder will drop out of the pins. Usually we see it on the filament leads. Every once in a while we'll see it over here on one of the grid ring pins, and the solder will drop out and then it loses grid reference, and then the thing just runs away and blows up. So we'll have to come back and address that as well. Okay, enough nitpicking. It's time to start testing and see what we got to do to modify. Okay, so the part that bugs me the most out of this whole setup is that there's no soft start on that full bridge rectifier. So yeah, let's put on some earmuffs. I want to get safety squints on here, protect my little eyeballs. You only get two, and the last time I checked, they can't replace those quite yet. So let's got our personal protection equipment here on. Safety squints, eyeballs. That is the hokiest plug in history, I swear. Okay, this is either going to work or explode. Whoa, I didn't even touch anything. What happened? Amp on. Plate meter not working. Got this set for AC. No volts. Okay, and it's showing 2,000 volts here. So what's our input voltage? 2,500 volts on the input. That's not right. Can't be right. 2,500 on the input. Let's go over here to the computer. 500 times 1 point. Yeah, we're low. And I don't think this meter's reading right. So let's go flip this over to DC now. High voltage is pulled off of this. So shut that off. At least the fan runs, right? And nothing blew up. All right, contactor's off. Let's disconnect this. I don't feel like dying today. Just don't. So it's neat to see this meter work. I don't think it's accurate though. I wanted to see that input voltage more than anything. The secondary of the transformer. So what I mean by input voltage is the primary on this transformer obviously is 220. The secondary is 2,500 volts, which after we rectify it should be somewhere between 3,200 to 3,600 and some volts. Okay. But over here on this meter, it's showing us 2,500 volts. Now it's showing this at 0. So dead and grounded. Okay. Hook that up to ground. That's not right. Okay, so now we'll switch this back over to AC. It's not too bad, but voltage is way low. 2,700. All right, let's take our ears off so I can actually hear. That's not right. Might have part of the string that's gone bad, a rectifier string. It should be way higher than that. If I got 2,600 volts going in, or 2,500 volts going in. Okay. So let's verify that it's making it over here to the top of the tube. So now according to this meter over here, we're at 500 volts. According to this here, we're at 1,000. This meter is way off. Remember, the top on our caps is 3,600 volts. We should be closer. We should be like 33 is where we should be. So our next option is to lift the legs of the secondary off, and let's measure that. God damn motherfucking son. We'll measure the secondaries disconnected from the diodes, because right now we're not seeing, just not seeing it. So let's remeasure this. $21. I thought that said 25. So 2,000 volts on the secondary of that, which after rectification, that makes sense, 2,700 volts. Let's see if anything down here is getting hotter any other than the bleeders. Nope. 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 Okay, so we have enough shmoo inside of this thing. This is way off though. We'll make an adjustment on that. Of course, we're gonna have to rebuild that whole circuit. But the bleeders are working. I wonder where we're getting our AC ripple hum noise from. It's gotta be from that. It's gotta be from that. All right, so the AC's off. That means I can touch that. But I'm not in a big hurry to stick my finger on the end of that cap. This reads 0. That means still there's 1,000 volts to go. So let's let it do its thing. I just, yeah. That's a full bridge rectifier that's in that. And no soft start. We'll have to see what it does under load. We'll have to see. All right, gents, so I just got done rebuilding the power supply. We'll come back to that. I had to put a soft start in it, glitch resistor in it, put fuses in it. You know, the basic minimum, like put a ground bolt on the power supply kind of thing. Changed over to real high voltage wire and not 600 volt wire, putting 3000 volts through it. So we'll come back to that. So now we're going to jump over to here. We're going to mono band the snot out of this thing. So that means we're going to pull all of this input and output coax off. Oh yeah, it just keeps getting better. The closer we look, the more problems we find. Yeah, that looks safe to me. This is, well, this one's tight, but if you could see the solder work on that, your Johnsons would cringe up inside your body. Okay, so I'm going to strip the input pass through. I'm going to strip this sucker down. We're going to pull off this grounded grid wire that's all tied together like gobbledygook. We're going to put 393 over here just because we can. It's not really necessary. We're going to put 2 brand new coax connectors on it, and we're going to put RG400 for the input and then pass through. And then on the back for the fan, we're going to do this thing. It's called use a grommet. Yes, a grommet. Amazing, right? I want to leak check this capacitor because of this right here. See this? That's the vent for this capacitor, and it is venting. So that could be part of our humming issue, but we'll come back to that. So needless to say, this is the last time we're going to see it like this. When you come back, the faceplate's going to be off. Well, I'm just going to do the McNasty on the bottom side of it, and then tomorrow I'm going to rip the coils and stuff out of it. So away I go. Oh yeah, good solder joint. Oh yeah, look at that. Oh, that's so sexy. Oh man. It gets me randy into boy parts. Let me tell you, look at that. Whoa. Yeah. So no ground here and no ground whatsoever over here. And I wonder why there was some arcing and sparking going on. We're not going to even talk about the beautiful sexiness I found over here at this joint over here in the back. This is the primary ground for the entire cabinet from the amplifier to the power supply. And it's supposed to be attached here. Well, I just tugged on it and it just came off. So this was never attached to anything. This guy's pretty lucky that he didn't manage to electrocute or kill anybody with this build. But moving along, just going to move along now. This is not the solder joint that you're looking for. This is not the solder joint you all are looking for. Hello, it's me again. This is where the RF comes off of our 3 tubes past our tuners. It comes out to the relay. I don't know if you guys can see it, but this little connection's a little discolored. And once again, we're going to talk about the arcing and sparking that was taking place. I think that might have something to do with it. What do you guys think? I don't know. I'm just not trying to judge anybody, but I personally feel that that might be a bad solder joint. I don't know. Just saying. Passively observing things here. Hello, me again. The longer I look at this, the sadder I just become on the inside. Got the back of the amp off now because, well, I just can't live with that being an opening for my airflow. So I thought, well, I'll just go ahead and mark a hole, and you know, I'm going to go in here and eventually trim all this out and make it look pretty. And I got a drywall screw holding this side in. Not one single nut or mounting hardware on this thing is the same. Not even on the fan guard, right? So if you guys remember, we had that big old wrap of wire that was attached to this lead, which was long enough to actually make it to the fan. No rubber grommet, by the way. I went and I pulled on the leads. And this is what the end of the leads looked like. It would just completely burn off. So I don't know how the fan was working. It was working. I remember hearing it turn and seeing it move air. These are our solder terminals for the fan. They are scooching pretty. Look at that. Oh, some technician needs to learn how to solder like that. I'm here to tell you, you got it made. It's all the little things that I'm starting to really kind of hop wise to on this thing here. Like, how is that? There's no strain relief here. The wire is just banging around on the inside of this plug, or this port. So, you know, this all's got to come out. I got to change that out so it's actually strain relieved and held in with pressure for safety reasons, right? The minimum safety to where nobody dies. I don't want anybody to electrocute themselves here, right? So let's look at our wire that our whole bundle comes out of. They couldn't just simply put a little piece of heat shrink on this? The bare minimum. Whew. Sorry, I had to bring you guys back for that. We're not going to talk about the foot pedal remote plug back here. This is a resistor. There are 2 disc capacitors. One of them is broken off and just floating off in free space. Ouch, that's sharp. It's got a sharp little burr on it. Ow. Probably got herpetogonosyphilids from it now. And this thing is just kind of folded back, and the wire for the pedal, this blue wire, is just kind of touching it. So this comes back over, and this is what actually causes the relay to close. So we've got a brown, gold, gray. Got something, 4, that's an inductor. This shouldn't even be here. This doesn't need to even be on here. Okay, now that I've documented how thoroughly messed up just the basic power plug is, let me pull this off. We're going to fix this. We'll fix this. We'll fix this. We're going to neaten all the wires up. Then we'll ground the grids, and then we'll do coax connectors. It just keeps getting better as I go. So I'm in here cleaning, right? Now it has been 4 or 5 days since I shot that last segment. So I'm feeling, I was telling the guys on Patreon, so I'm starting to feel like a country western song. So the only thing left that could possibly go wrong over here is that, like, my Chevy breakdown, right? I've had, my wife had a tragic loss with her animal, her horse, and some of the things that we've had go on there. And then I went on this road trip, and I come back home, and my grandma has been not doing so well, and she ended up losing her fight with life here this last week. So I've been off dealing with that. I've been telling people, I said the only thing left that could possibly go wrong would be like my dog left me, and my Chevy truck broke down, kind of thing. So I thought, well, it's time for me to get back in the saddle and get back to work. So I thought, man, I'm going to give this a good clean and get the grids all grounded up on, get this ready to go. And so far the theme has been, the longer I look, the worse it gets when it comes to this amp. So I'm out here trying to clean the burn mark out of the back of this amp and scrape all the flux out of this thing. And I noticed this. Not only was the output wire for the output not soldered down, this is the board that your input signal comes in. You attach the ground to your coax here, and then the center conductor goes here, and your input RF goes through this disc capacitor, and it comes over here and gets injected onto this filament lead. How does the RF make it in the box if the wire off the 0.01 isn't even soldered down? Now, we're not going to pay attention to this this little piece of board, how it's busted, because, well, that's not a big deal. I can fix that. I got glues. We can fix this. This isn't the problem. It's this here. It's the little shit like this that'll make and break your amp, right? We're not going to talk about the bad coax and all the other stuff that we've had to overcome in here. But this right here, this wasn't even hooked up. Well, let me get this cleaned up and get most of the burn and most of the old flux off of here. I got to get these eyelets all cleaned up and get them prepped up because we're going to reground the grids. The grids were technically grounded on this thing. Technically. The problem is they were soldered together like the rest of this. It's just been bad solder joint after bad solder joint after bad solder joint. Kind of like the strain relief. Yes, there was technically one there, but there wasn't half the part there, so the wire's just banging around on the inside of the strain relief. Or the wire loom, the way the wire loom was terminated, it was just raw wire hanging out. Our ground wires, they looked like they were soldered down, but they weren't. So there was no good solid ground between the case and the power supply. So I rebuilt that, soldered everything appropriately, put heat shrink on the end of it. There's supposed to be a switchboard that's here, it's a multi-terminal board that sits here that allows us to switch between the dual 110 filament leads, or not filament, but dual 110 primary leads on the plate transformer. That's why we can tie them together, and we can have our 220, or we can put them for 110. That board's missing, so I came along and I created this piece of phenolic to help support this wire instead of zip tying it to the case the way it was before. Make sense? And then I went in and resoldered these because I don't trust any solder connection in this box now. Zip tied it up, so now the wires are all supported coming in and coming out of the amp. It can't move. That's what we want. We don't want it to move. Okay. Let me finish getting this cleaned up. I got to blow this out with an air compressor now. And then we're going to ground the grids out. We're going to clean up some of the wiring underneath here. We're going to add a new wire for the remote on-off pedal. It goes over here to the relay. And we're going to start turning this project around. We're going to get one thing done after another. Power supply is 99% done. Now let's start working on the RF deck. So we're going to finish this up the bottom side. That means we've got to put 2 new coax connectors on it. We've got to wire the relay and create a new input network for this. And then we'll flip it over and then we'll do the top side. Okay, so now I'm on the top side of this box. I'm getting ready to pull the face off and start doing that stuff. The bottom side of this is pretty well all prepped up. I'm to the point now where I've got to pull the top off to get the band selector out and get all the output network off, but it just, the longer I look, the more problems I find. It's like, I'm glad I'm completely redoing all of this stuff. This strap here should actually be on this coil and should be attached to that nub. So somebody's tried to retune this. And then there's another small problem. Ready? I don't think that's any good. Something says to me in my mind's eye that eventually could lead to some problems. I don't. Anywho, all right. I'll pull tubes out now because we're to that point. I'm going to be flipping the cabinet over a bunch, and I don't want to be jostling the tubes around. So we'll pull these RF parts tubes out, and we're going to pull the faceplate off, and we're going to take the guts out of it because none of that needs to be in here. And it's, let's face it, with this and this all being modified, I'm definitely not taking from the amateur community in any way, right? This is all the stuff I've had to take out of it so far. And there's going to be more on that pile before I'm done. Just saying. The Allen set screw in this is way too loose. That's our anode tip. This is our anode tip cooler. That's how it was when I took it off. Scary. Scary. So, let's go over here and at least the finger stock on these sockets is tight. That's a plus. Well, that one's tight. All right. All right. Oh, oh. That's good. Don't worry about it. We're not going to worry about that. Let's move this out of the way for now. Yeah. Maybe some of the buzzing noise that they heard was almost every single thing that had anything to do with RF coming in or coming out of this amplifier had a cold solder joint on it. Maybe. Just maybe. Got myself a clean canvas to work with finally here. Look at this. I keep digging solder flick out of this box like it's free or something. It's just everywhere. Well, I pulled the band selector out, and the 11 meter portion on the band selector is burnt. I mean 10 meter, sorry. And the 10 meter input section on this is burnt too, but it's all good. Let's take a quiet moment and clean the 25 years of cigarette schmoo off the inside of this space. I gotta have me a clean space to work with. I mean, I gotta have it. Can't stand getting the nicotine slash cigar slash marijuana slash crack high off this every single time I touch it. Let's give ourselves a prayer of making this work right. Gotta make it look pretty. Believe it or not, me cleaning this up, it's more about the operation of this thing than it is about looks. We could have this thing be brown on the inside and it wouldn't care until it decides it's going to arc over on a tune and a load fin, and somebody call me and crying, "Man, I load this thing up, it arcs over, what the hell?" I mean, really, what is 5 minutes? I mean, I'm taking 5 minutes of your life right now just to show you this segment. Man, that is some cheesy ass. That'll get out the isopropic alcohol and douche this all down and blow it out with an air compressor. Okay, so I got the whole bottom side of this box rebuilt. Got a new cap over here for filtering cap. The other one was bad. Had a suspicion of that, as I pointed out when we first started. Got all new RG400 and everything. Brand new input network. Now we got this piece of paper in here to close the relay. My network analyzer is attached to this piece of coax, which comes in, goes through the relay, comes out, hoops around, goes through our input matching network, and then goes out to the 3 tubes. The 3 tubes are in the amp. Now the 3500Z is a fairly cool tube because we don't have to add any resistance to it to be able to demonstrate our capacity. There's no resistive load that I have to add to the bottom of the tubes to emulate it in operation or simulate it in operation. So of all you newcomers, a lot of you guys are not, but for some of you newcomers, what we're looking at, this is frequency. And as the signal dips down, the lower we go to the bottom of the chart, the lower the SWR. So over here, on the far left-hand corner, is the green S. So that little green hash mark there, the little green tag, that stands for 26727 freq. Okay, we're centered on 27.025, and where we're currently at over here on the bottom end, the right-hand corner of the scale, is 274783. Now this amp is going to a guy that does a lot of sideband work. Well, as we know, the sideband side of things is all in the upper channels. So I want to give him the ability to work up in frequency, you know, let's say 80, 90, 27, 80, and down to 2650, okay? Give it a wide span. So he can adjust this amp by turning the knob in the front. We've added a tuner where the band switch used to be, right here. And as we adjust that tuner, the input frequency response is going to change. So right now we're at like channel 28. I'll slowly roll this down. So we have an input SWR of 1.051 at channel 47. Let's go ahead, we'll walk this across. Anything below this line is below 1.2. So by the time we get all the way down here, which is well outside of the band, 26, let's say, we're at, come on, we're to 1.21, which is really good. So we'll roll it back over here, and we'll see once we get down here towards the bottom end, channel 6. That's about channel probably 15. Probably about channel 20, channel 30, channel 40, and on out channel 50 and on up. So now we're looking at basically 26 to 27 megahertz roughly, or 27.5 megahertz roughly. That's our frequency response. Now if I take our span and let's jump it out to 10 kcs, and now we'll go ahead and we'll span this out even further. We'll go to 100 megahertz. So from 0 all the way out to 56 megahertz, that is our input, basically a filter. The only place that this is going to allow any RF to go through is on the precise frequency that you're on. That's how we guarantee we don't splatter and we don't jump all over all the other channels or other frequencies. Okay, but as we can see, as we spin this knob, let me crop this a little bit. As we spin this knob, you can see it moving back and forth. See that? So we'll do span again. We'll go to 10 megahertz wide. And we want to have it this tight of a roll off. This is our desire. So now we're reading from, this cursor is at 26 megahertz. We want to have this tight of a roll off. That way we can start up with a frequency trap and we're not going to have to worry about spurious RF emissions. And by the time we're over here, it's 28 megahertz. I'll bring this next one over here. It's 25 megahertz. So let's roll the frequency over. I wouldn't want to take it anything past about yay there. It's like 1.3. So it'll work from the very bottom of the ham band to about 26,291, which is kind of cool. You can see the butter zone's right in the middle. Where exactly does that land? So all over that input network on this is perfect. Let's go look at the output side of things. So the output side actually starts here on the bottom. Where this used to pass through was a big open hole. There was no grommet. So I went ahead and opened the hole up a little bit more and we put a grommet in here so that the termination point on our tank coil, there's no way it can arc into anything. It can't move around. It can't bump into anything. This little piece of wire here that's running over to the relay, we're going to capitalize on the fact that you can carry more current over a small distance through a smaller piece of wire. The reason I'm using this gauge of wire is because I wanted it to go through the eyelet and wrap all the way back through and be able to fold it over and get a mechanical connection along with an actual electrical physical connection. So I had to get in there and do quite a bit of scrubbing, but I was able to get the tin to show back up underneath all that burning and arc mark that was inside of here from the old output network hooking up to the relay. RG393, can't melt it, will never burn, never fail you. Okay. So we got that figured out. Now, let's flip this thing over and let you guys see the top side for the first time since it's been completed. What we got going on here is what we call simulated load, emulated load. We're going to go ahead and we'll hook up our network analyzer to the output of this thing. And hopefully our little piece of paper didn't fall out when we flip the amp over. We'll find out here pretty quick. It did not. So we put a brand new blocker in here, 3 times a kV, and we did that for a reason. And this guy's probably going to drive this box a little bit hard. Plate volts are a little bit low, so you have to drive it a little bit harder. I wanted to really make sure this never fails him. The little Sprague doorknobs, like what we see over here, they have a tendency to collect moisture and then go short out and blow up. So we took and moved the tank coil, or the tank coil, or plate choke, and put it down here closer to the tubes to decrease the inductor length from here to the rest of the tubes. We want to keep this length as short as possible at all times because it dramatically affects some parts of the other circuit. We have each one of the parasitics at its own different plane, and then we have the emulated operational resistance simulated by these, let's see, 1,500 and it's 1,566 ohms, so I've got 1,500 worth of resistance here, 1,500 ohms. So here we are again. Let's check our span. Let's set it for 10. We're at 10. So our meter is reading from, survey says, let's see, 31 megahertz to 26 megahertz roughly. So once again, in the middle, we'll say our desired frequency that we're going to want to operate this thing on is 27.025. Okay? It's the same thing that happens when you tune the amplifier up. As you're adjusting your plate and your load, to be perfectly in resonance. All I was doing was simply tuning these back and forth. Watch my fingers how much movement I'm putting into these. This tuner is an RF parts upgrade tuner that they sold 1 billion of these things. And in my opinion, there's too many plates, and in my opinion, the plates are too close together. It makes your load knob very sensitive. Let's just go over here and we'll totally fart with the plate. Look at how small I'm having to move this. Like if you guys can even see my hands moving it. It's that small. So very small movements. My homeboy, who's a needle bender that's getting this thing, he is going to get it with it pre-tuned, and there's going to be tape on the knobs. So as it's being hand delivered by another one of our needle bender buddies, when he gets it on his end, it'll be fairly close. So it should be fairly quick for him to tune it in and just be able to take off and run. We replaced all the old stanky ass high voltage wire on this thing. Let's turn this thing sideways so you can get a little better look at it. I cleaned the guts out of it. I cleaned all the tubes off. Replaced everything that was dangerous and deadly in this thing. Cleaned up the metering circuit and made it so it made a little bit more sense. Cleaned up the plates so it didn't look like it was hacked together by a kid with a handmade file out of a toothbrush. Build them a whole new tank coil, brand new blocker. This bypass cap. I wanted to cover that. I pulled this apart and I start looking at the bypass cap, and it's already failed. So I pulled it out and replaced it with yet another Sprague 1000 puff. And where we're going to pass the high voltage through, we went ahead and put it through a Heiko connector. So we'll bring that through on 15 kV wire, bring it down to this doorknob that's in here, so if he wants to disconnect it, he can. I am not giving this guy the ability to unthread and rethread at the back of the box, the high voltage lead. To me, that's just stupid and dangerous. When he receives this, because it is getting hand delivered, when he gets this on the other end, the high voltage lead is going to be attached inside. I've had probably 4 or 5 horror stories told to me in just the last 2 years, and we're not saying these are people that have died here lately, but have died in people's recent memory, where they have that screw-on connector at the back, that standard, what is it? God, I just had it on the end of my tongue. I love it. Anyhow, the Molex connector that was on the back, the standard Molex connector, those are good for inside of an enclosed space to disconnect and then pull the RF deck out. but with the umbilical running in between, I don't like doing these. That's why I've got not one, not two, but 3 separate ground wires going from the power supply to this cabinet through that umbilical. And the positive side, we're not going to even give you the option to get into that, like to be able to unscrew this or have to reach back and check this ever. And when you see how I have the positive wire set up, you'll understand. Okay, so my next step on this is I want to clean up the fan mount here on the back. We're going to hook up our fan wire, which is just the smallest things that we ask for in this world, I feel like, for safety's sake and electrical sake. Now, the fan lead comes out, doesn't go through 25 feet of speaker cable, and it's going to go directly to the fan. Well, one of 2 fans. You'll see what I mean. You'll see what I mean. All right, let me get the whole thing put back together. Let's get the face on this thing. Let's get the fan on the back of it. Let's get the knobs mounted up. Let's get our paper pulled out. Let's get this taken off. And I think it's almost time for us to run it. Well, we're almost at the end of this thing. So we've got our on-off switches are all working. Power on-off. I got to put another light bulb in this one. Apparently it's gone bad. I've got my high voltage on and off. And we'll come over here and we'll look at the power supply in a few minutes. Radically different and a whole lot safer. So what we got going on here is our clip over amp ring, and that's on our positive wire. Now, I had somebody once said to me, you can't use that kind of clip over ring. It's only insulated for 500 or 600 volts. It says so right on the amp ring. Okay. Yeah. That means the plastic in the unit itself is only an insulator up to 600 volts. I said, well, current is current. That's a clamp over amp ring. It's measuring current. Doesn't mean you got to have your dick beater on it. All that amp ring means is that they're gonna guarantee that if you clip that over a bare wire, it's not gonna conduct. Well, we've got this going through, oh, what is it? 40 kilovolt wire. This is 40 kilovolt wire, okay? Nice high-end silicone wire. So all I'm using it to do is measure current. All I want to see now is, because we're finally at the point where we're getting all the systems to come together. The tubes are all lit up. We got the right filament voltage on the tubes. Everything's kosher. Now what I'm wanting to do is make sure that this relay is working, and I want to make sure I have bias flop. Well, how do we tell if we got bias flop? Well, we measure it. There's a couple things. We're going to measure our bias by our amp draw on the power supply, but we're going to look at the voltage that's present on the tube in the flop. So right now, if we take our voltometer, let me get this hooked up and then I'll see if I got it all in frame. We're going to take our ground lead and we're going to hook it to the case. And then we're going to hook it to one of the filament leads. And it's going to show us that there's 120 volts DC present. Now there's no high voltage present on the power supply. High voltage is off. High voltage is off, but when I step on a pedal, watch what happens. Drops to 1.6 volts. So that tells me my diode string, all the diodes are oriented in the right direction, and it's ready to do its job. And normally I want to shoot to be around 3 volts. But remember, our power supply that came with this particular setup is a little bit low, in my opinion. It's only got one tap on it, and after it's rectified, we see a total of 2800 volts on the plate. So I can go ahead and I can pull the bias a little bit lower. That'll allow us to get a little bit more schmoo out of the tube. So that's test number 1. I know the relay's working. I know I've got access to the cathode through the tube, or through the tubes, because there's 3 of them, right? Anode top part, And the only way you can have access to the cathode is through the center tap of the filament transformer. So I know I got my diodes set up appropriately, and that whole circuit's working. RF's coming in, step on the pedal, click, now it's going into the tubes. And the output of the tube network is now tied into the output coax. So now what we have to do is we have to test this. Let's go ahead, we'll kick on our high voltage. Now when we step on the tube, or step on the pedal, it's going to activate the tubes, and they're going to go into actual operation. 300 mils, which is perfect. You want about 100 mils per tube. So 0.3, that's 0.3 of 1 amp. It's perfect. That's what we're looking for. And you can also hear the power supply starting off because it's working. Okay. That also makes me happy. Now we'll rapidly bleed off our our high voltage by activating our bias. Now, never in the time of man is it more dangerous than what we've got going on right this second. I don't have a meter showing me what's left in the capacitor. So we're going to step on this pedal for a few more seconds. Help bleed it down. You do not know a circuit is dead until you can measure it and verify and then ground it. So I got to get the meter circuit working. But I'm stoked because one, the back's on it, the fan's reinstalled. The auxiliary port for the new fan that you guys haven't seen yet is also installed. All the labels are on it. Relay's working. Our output network's all set up. We're like 2 seconds away from being able to run this. So let's go over here and look at the power supply. So I decided to add some safety circuits to the power supply. I personally have a problem with not having a breaker, a disconnect, or a fuse of some kind somewhere on the 220 side of the circuit. That is inherently very, 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 very dangerous. This had none of that. So in here is two 15 amp fuses on the 220 lead. Will this thing ever pull 15 amps? No, not in its wildest dreams. Can't, just physically can't. But we do have a disconnect from the wall to make it minimum safe. Now, we've gone ahead and we've added, I've got this labeled at 5 amp. Right now there's only 1 amp worth of fuse in here, but it will be a 5. We've added a fuse on the ground side of the high voltage circuit. Okay? Well, we've also tied to the ground lead of the contactor, which is in the back. Contactor back here. So if there's a short or something arcs over or one of the tubes decides it's going to go bananas and run to ground, it's going to show an excess load of current. It's going to blow this fuse and it's going to disconnect ground. So the power supply, all of a sudden, the filtering cap and the whole rest of the circuit no longer has a ground reference. Well, guess what? The contactor is also going to go bink and shut off, which turns the transformer off and immediately kills the high voltage. And the bleeder circuit then can bleed off all the high V. I have a problem myself with somebody that's willing to say, yeah, that box is good to go, when there's not a single fuse, a disconnect, or an isolation circuit of any kind that's going to automatically pull the high voltage off when it sees a short, that it's not going to give us a fuse into the cabinet. And then the other thing every amp must have is a glitch circuit. See that? See that bank of resistors? What we have there is a bunch of 15 ohm, 100 watt resistors. Well, with seriesing and paralleling them, let me move the camera over and you can see what I did back here. With a bunch of seriesing and paralleling, there's, let's see, 1, 2, 3, 4, 5. There's 1,000, or there's 5, there's 500. So total 1,000 watts worth of dissipation, worth of load, but it's at 1.5 ohms. So there's just a little tiny bit of resistance in the positive side. Once again, why do we want to have that inside of our power supply? Well, if we have an arc or a short over, in our amp or in our umbilical, instead of wiping out your diodes and totally destroying the anode on the tubes from the electrical pulse, these resistors are your sacrificial animals. They act as an electrical shock absorber for when that huge arc comes flying back. All that free roam energy comes flying back. Instead of it running right back and wiping out your diodes, the resistance in these resistors will dissipate all of that energy. Protect your power supply, and it gives you 100% protection on your tubes. And if you have an arc in the cabinet, it's not going to run back to the cathode because of these resistors. The resistors are going to suck up the differentiation in voltage and current that becomes present with a hard arc. It's going to help protect your other tubes, help protect your power supply, and it's going to help after this fuse blows. Now everything's isolated. Make sense? This is what I call minimum safe. There's even more circuits that if I was to build this, like full-blown build it, there would be safety interlocks for the lid on this cabinet, safety interlock for here, which I'm going to re-engage, which I'll show you here on the top side in a second. But I went through and I completely redid the power supply. Everything is on 15 or 40 kVA wire, totally insulated safe. Tripled down on the ground that goes between here and the cabinet. And I actually added a ground nut on the back of the cabinet, and the ground nut that was on the back of this cabinet wasn't even tight. So now it's got extra mounting hardware and a new nut over here, and we got a new nut and grounding hardware over here. So we can actually run a committed ground separate of this umbilical between A and B. It's called minimum safe. Okay, let's flip the thing over. Let's flip the RF deck over. Let's get the metering circuit working. That little guy for our high voltage. And I think it'll be time to load it up and test it. God, I'm stuck. I feel like I'm unstuck. I feel like I was stuck on this friggin' amp for... It's just because all the drama I got going on over here, and it's all done. Yay. Get back to work. Okay. I'm excited because this thing's working fairly well for what it's got on it for plate volts. First thing I want to cover real quick on the fan. The fan had self-tap screws, and the fan was held in there with drywall screws, if you guys remember. Now it's got all matching hardware. The hole's been punched out perfectly. We increased our airflow, and it's got 632 thread with crush nuts holding this fan in place. It's not coming off. It's done right. The mounts that go down the middle of the cabinet for the top lid. This one, were all stripped out. So I went in and I drilled them out and replaced them with aluminum crush nuts. All the hardware on the outside of the cage, the outside cages, have been changed. It's all now got stainless steel, and it's also got crush nuts in it. So that makes me happy too. Crush nut, crush nut, crush nut. The thing is actually pretty top titties, pretty notch in my opinion. So let's see here. I was able to get the voltage to trim up on the meter. This does sit 2 ticks above 0, and that's because the needle is bent. And I am not going to pop this lid off and run the chance of breaking the needle on the power switch, or on the power meter. So let's go, let's turn the amp on. And we're resting at 2800 volts, and that's where that meter is resting at. It's 2800. So we're going to gauge, and it's dropping to about 25, 26. Let's get the camera on that. 26 volt, 2600 volts. Okay, because we have this lower voltage, we are not going to see the massive 4,000-ish watts that we saw out of the other amp, the other 3-tuber. I have no idea where we're going to end up, but I do know this for a fact. The input tune on this thing is smoking sexy hot flat. The pass-through on this thing is smoking sexy hot flat, and it's making fairly decent power. So let's show you with a little bit of drive. I don't know what it's going to do with the 2-pill driver yet. We'll find out. Let's get ourselves some measurements set up here. It's a 1000 watt slug. We're in 1X, that's in PEP. This one here is a 1000 watt element in average, and the 5 watt slug in reverse from the Bird 10,000 watt dummy load. Let's first show you radio power. At 012, putting about 110 watts into the thing from the derail striker 955. Show you our pass-through tune, and what I mean by that is the RF coming from the radio, passing through all the connections, going through the relay, and coming back out to the dummy load. 11111. Here's the 5 watt slug in reverse at 01111 at 01111. A whole lot of no action going on there. Okay. So our amp is on. We'll step on the pedal. At 012. At 500 Bird, and we're pegging the 1000 watt slug in the corner. Let's go up here and let's look at the input tune. See what the infamous striker says. 111111. 1 bar. 1 bar. Let's see what the Bird meter actually reads. At 012. So 2/10 of 1 watt with 110 watts going in. At okay. Now we just saw it rise, correct? Well, what I did is I reached over and I turned the knob for the input tune. And I brought it up. Oh man, that'll make everybody sick in TV land. Brought it up to dead center. So now, let's go ahead and we'll translate back up here to the input reflect meter. Hello. Let's tune our knob and watch our input reflect drop out. Hello. 1-2. Oh, about 1/10 of a watt. And where we have this knob adjusted, directly at the 9 o'clock position. And that is because this is way low on the, or no, this is right where it needs to be actually, come to think about it. Right in the 9 o'clock position. The other 2 tick marks, this is how they're orientated to get the power out that we're getting out. Remember, our plate volts is low, unfortunately. A couple hundred volts low. But let's go over here. We'll click that up to 2x. So now, as you guys all know, man, I did. Where's my pointing laser? I don't want to reach across this damn amplifier. Okay. Graduated Sharpie device. About 4 lasers. Left them scattered around the shop, and none of them are where I can grab them. When the meter is here, that's 1,000 watts. Fully all the way here in the corner is 2,000. So 1,000, 12, 14, 16, 18, 2,000 watts. So let's see where we end up here. That's going to bug me. As soon as I get off camera, I got to go find my lasers. It bugs the shit out of me. I bought too many of them damn things. All right. 110 watts of drive. At 012. At 012. So 1,400 watts with little to no strain or pain or effort. Let's go over here. Let's take a look at the spectrum analyzer. Radio. Amp. Okay, so I got the bench 4 pill hooked up. I'm running the derail striker with a variable bird and variable peak. That's full wide open. Audio. No matter how much louder I yell on the mic, it does not make any difference. So we got a variable peak knob. If you got a question about that, go see the derail bench radio video. It's pretty cool. Okay. 700 watts of drive, which is crazy in my opinion. I'll step on the pedal. Now we're on the 5,000 watt scale, so we're reading a middle scale. The 10, the 20, the 30, the 40, the 50, and we're adding 2 zeros. Hello, 1, 2. Hello, 1, 2, 1, 2. With 500 watts of drive, this thing makes 3,000 watts spot on the money. We are running completely out of power supply. I'm going to show this to you in a minute. But with about 600 watts, 600 to 700 watts, hello, 1, 2, 1, 2. We're 3,300 watts, which in my opinion is a little low. But we all know why. Let's come over here. You guys are going to get a kick out of this. I'm getting a kick out of it. We're making 3,500 watts. Hello, 1, 2. Hello, 1, 2. With 2,200 volts on the plate. I don't know who built this, but in my opinion, they didn't do too hot of a job on the. Well, they didn't do too hot of a job on a lot of different things, but the power supply is definitely inadequate. So. Now I'm here to tell you, I did turn the drive up on this thing, and it hits a brick wall at 3,500 watts. Just crash and burn, 3,500 watts. It won't do a drop more than that. It just won't. So now I got to turn it back to the customer and see what he wants to do. I do have a little bit bigger transformer sitting here. Let me see if I can get that out for us to look at real quick. Okay, so this is a 1 1/4 amp transformer, and its secondary is 1,200 or 1,800 and some volts, which is 3,300 volts, which is 600 volts higher. The question is, I don't know if I can get it to fit in the power supply. Okay, let me see if I can do some shoehorning here. I stayed up and pushed myself till 5 o'clock this morning working on this. I removed this transformer, which is about half the size of that transformer. This thing hummed and buzzed and was just not happy to be present in this situation. And it would not hold above 2,100 volts no matter what we did. It's too small. The other thing we did was we removed the filter bank. It was too small. Got rid of it. Built a whole brand new filter bank over here for this thing. So now what we got is we got this situation. And that's accurate, believe it or not. It it pins that thing in the corner. But see, that's all fluff and circumstance. Once we put a little bit of load on this, now we're getting realistic numbers. Okay. So we're sitting at around 3,000 volts at idle. That's at zero signal with bias applied. As you can see, the bench 4 pill is now gone, and we're on the bench 2 pill. We've got our voltage turned down about as low as we can get it to go. Got our 100 watt striker. Let's go over here and let's take a look at the watt meter. Hello, 1 2 1 2 1 2. Hello, 1 2 1 2. About 350 watts. 370 watts peak. Let's reach around here and not electrocute ourselves. We'll flip that down to 5x. So now we'll bring the 3-tuber in. Hello, 1-2. It's 2,900 watts peak power. Hello, about a 600 watt, 700 watt dead key. A little 2-pill hitting it. You guys can remember we were doing everything we could with the 4-pill to keep it slowed down enough as it's 600-700 watts to achieve that same power level before. And the transformer doesn't hum anymore. That fucking thing doesn't hum no more. So let's go down here and let's turn our voltage up on our driver. And this will get us about 500 watts out of this little 2-pill. We don't want to run it any harder than that. It's kind of pointless. Hello, 1-2, 1-2. Hello, 1-2. Hello. Hello. 3,400 watts. You want more? Put more drive in it. Now 3,800 watt box. About 700 watts of drive. There's no point. So this is a situation of we're working with what we've got. I called the customer this morning and we talked. And I said, are you interested in ordering a new transformer for this? He says no. If it was me, I would get a different transformer than this. It has a little bit more amps to it. And then he could drive it a little bit harder and get more watts out of it. We'd get probably 4,200, 4,300 peak out of this. Pretty reliable. Here's the neat bit though. With the way this thing is sitting, as I'm sitting here monologuing, let's talk and I'll give you a visual demonstration. I'm more worried about my 2-pill than I am this amp. Let's take that and flick that to there. We're just going to lock this down for a second. So we're throwing a 1,000 watt carrier out there right now. Look, what he has said to me is that he wants 3,000 watts max out of this box, and he's perfectly happy with 3,000 watts. I said, cool. Then this thing has met your desired wishes. Now the tubes are finally starting to heat up. Look. 2 bells. And they'll just sit there. Power supply's right. The cabinet's right. The tuning deck portion of it's right. This thing is correct. And the tubes are good. The tubes are at where they should be. Now, that's without air. That I held that key down for that long. The customer is perfectly happy with where we're at with this build. He says, well, what would you do? I said, I wouldn't even build one of these. I'd do something completely different, a pair of, 800s, or for this power level, a pair of 800s, or by the time it's all said and done, if I built one of these myself, I'd just build a 3000, but he's happy, so therefore I'm happy. And in the future, if he wants to upgrade the power supply or do something different with the power supply, that door is open to him. So the main goal was for me to go through this and make it safe. Make it safe to operate, get rid of the hum that was coming from his bad filter cap system that was in the power supply. Make it so he could use it, and I'm surprised this thing even worked. With all the stuff that we found that was broken, not soldered together appropriately, all that kind of stuff. Blows my mind. that this thing was running. And let's talk about air. I got one more thing I've got to add to this yet. Let's go ahead and we'll shut this down. We'll step on our foot pedal to help the bleeders out. Oh yeah, and before the naysayers get involved, it does have a bleeder bank in it. Just takes its sweet ass time. Step on the foot pedal for a couple seconds and it drains it down to 0. Okay. When it comes to the 3500Z in this cabinet in its current configuration, I get a little nervous about the pins on the bottom and the plate and the filament choke. The filament choke has got me a little concerned. So what I did is I developed this for him. Little flush mounted fan that's going to woof some air up on the bottom side of the deck, up on this side of the deck. It's going to blow air across the pins and the filament choke. Just saying. So let me get the lid put back on this, and let's get the cabinet body, the armor and the feet put on this thing, and we'll get it all put back together. The other thing is I removed those stripped out mount points for the feet and did crush nuts on that as well. So we'll have a nice, good, solid thread, something to hold on to the hardware when we go to put it into the box. So, all right, we'll be back. I want to show you guys this really quick. This is all the parts that were broken, bad, or didn't need to be in here. Most of them were all broken or burned up, as we very well documented, but that's all the junk that came out of the amp head. Let's see. Here is all the hardware that I changed out that was either stripped or bad or just not right. That came out of this. I'd save all of that. All right, here you guys go. Let's wrap this puppy up. This has been a compromise, I feel, but I'm going to offer it out to him and he can go run this. He's not going to have any problems. Set myself up for expansion over here if I wanted to. And what I mean by is if he chooses to in the future want to order a new plate transformer and get the extra 1200 watts that are laying in this box, we can go order him this transformer, and I've got it set up so all we got to undo is 4 wires, 4 bolts, and we can put the new transformer in its place. I've got everything in here scooted out to the edges, and I laid down the groundwork, and if he wants to expand or upgrade in the future, we have that option. So this has been a trial for me in patience. Normally this would be a 2 to 4 day build, this particular thing, and this has been stretched out over weeks. Go ahead and shut the high voltage off. Step on the pedal, help bleed it down to 0. One of the other things that I did is this is dual armored 40 kV high voltage lead. So it's 40 kV silicone high temp, high blah 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 wire, and then it's got 2 layers of this nylon, whatever this is, wire guard on it. So it is the same length as the umbilical that goes from the power supply to the amp head. This has got triple redundant internal grounds between the power supply and the amp head. The high voltage lead and the ground leads cannot be broken from the amp head or from the amp head to the power supply. So there's no potential electrical shock points in the back. Right now we have a piece of 8 gauge wire going from the back of this over to the back of this. I would strongly suggest we do something like that on the other end before we go to use it. As you guys can clearly tell, there's a new fan that's on the bottom of this. And it's just down there slowly chooching air on the bottom of the pins of the tubes and cooling off that plate choke. But as you can see, we'll just look at the RMS meter here. It's kind of peeking around the side. I'll grab the foot pedal for y'all. Oh yeah, all right, kick on that high voltage. High voltage is helpful. We'll throw a 1,000-watt carrier out there. Listen, this box is stout. It's got a ton of good parts in it now. It's got a really good tank circuit. The tuning circuits are great. The input network is pretty much bang on. There's a coil that's on the bottom that I showed in a previous segment. If you can't get it to dial in perfectly flat with the tuner, you might need to spread that coil out just a little bit. We're talking just like that. And remember, this amp was completely tuned with having 12.5 feet of coax between the driver and the amp, or 12.5 feet between the radio and the amp, however you want to go about powering it. This is solid. This thing isn't going to melt down. It's not going to quit, and it's not going to give up. Power supply is not humming. There's no more hum in this amplifier whatsoever. So I'm going to consider it a win. Inputs all rebuilt, relays all rebuilt, output networks all completely rebuilt. There's been a ton of safety upgrades. It's got a ton of air moving through it. Customer's happy, I'm happy, and I want to say, gentlemen, thank you for tuning in and following along and being patient. Believe me when I say to you, all of you, I've got a ton of content coming for the rest of this month. I'm going to be busy, busy, busy over here, so get ready. Everything that's been backlogged for the last month and a half as I've been off dealing with family issues and deaths and other deaths and family deaths, I'm back. And the ball's going to keep rolling. And I appreciate everybody's support. Thank you for tuning in. Big shout out to Siglent. They're very helpful in this video having their test equipment. Big shout out to XS for the power supplies and the batteries that are underneath my workbench. Big shout out to Bird for giving me such access to wonderful, wonderful metering systems. Big shout out to Coaxial Dynamics for giving me access to all the accurate and free calibration of all my slugs and my elements. Big shout out to D-Rail over at Wolfman CB Shop for creating the workbench radio that I'm currently using in this particular video. Let's see. My friend Sean in Arizona that sold me the high voltage wire that was used in this video. Big shout out to him as well. Big thanks to my Patreon supporters that allowed me to keep the lights on the last month and a half. And seriously, if you guys haven't joined yet, please think about doing it if you've ever learned anything from me. And a big thanks to all of you guys. On that note, these 2 boxes of garbage are now polished, and they're good looking diamonds, and they're going to run forever. I appreciate you guys, I really do, and I say it over and over and over again, and I mean it honestly. I'll see ya. Click, click.